8 minutes ago, on a mountain in Chile, a telescope finished another image. And before I explain what is inside that image and what this machine has been doing since it officially switched on just weeks ago, I need you to understand one thing that the headlines are almost universally getting wrong. This is not about a single discovery. This is about a machine that is going to make more discoveries in its first year than every other optical telescope on Earth has made in all of recorded history combined. Not close to that number, more. And the survey it is running has been officially underway for only a matter of weeks. Let's go through exactly what happened, exactly what was found, and exactly why the people who built this thing are still, in their own words, struggling to take in the scale of what they have switched on. The observatory is called the Vera C. Rubin Observatory. It sits on the summit of Cerro Pachon, high in the Chilean Andes at an elevation of around 2,680 meters. The location was not chosen casually. This particular mountain sits inside one of the driest, darkest, most atmospherically stable patches of sky-accessible land on the surface of the Earth. No cloud cover to speak of, no city light within practical interference range, no moisture hanging in the air to scatter or blur the faint light arriving from distances, measured in billions of light years. Astronomers have been studying potential sites for this instrument for decades. This is where the numbers pointed. The telescope itself has a primary mirror 8.4 meters across. That is roughly the same as the width of a tennis court is long. Attached, behind that mirror is the camera, and the camera is where the engineering story gets genuinely hard to process. The LSST camera, built by the U.S. Department of Energy's SLAC National Accelerator Laboratory working alongside teams from institutions around the world, is the largest digital camera ever constructed by human beings. It weighs approximately 3,000 kilograms, roughly the weight of a small car. It carries 6 optical filters, each capturing a different band of light from ultraviolet through to near infrared. And its sensor contains 3,200 megapixels. Your phone camera has somewhere between 12 and 50 megapixels. This camera has 3,200. A single full-resolution image from this instrument contains so much data that displaying it at true resolution requires 400 separate 4K television screens placed side by side. Not displayed smaller, not compressed. 400 screens just to show one picture. And this camera takes a new picture every 40 seconds, all night, every night, without pause, swinging to the next patch of sky, capturing another image, swinging again. Each image processed through calibration layers before entering the official data pipeline. Each night generating approximately 20 terabytes of raw data that travels from the mountain in Chile to the U.S. data facility at SLAC's National Accelerator Laboratory, where it becomes available to the global scientific community. The mission behind all of this has a name. The Legacy Survey of Space and Time, shortened to LSST. The plan is to scan the entire southern hemisphere sky continuously, revisiting the same regions every 3 days for 10 full years. What you get at the end of that process is not a photograph. It is a movie. A real data-gathered, observation-based movie of the night sky changing across a decade. Scientists have literally called it the greatest cosmic movie ever made. And on June 30th, 2026, the camera started rolling. Before we talk about what has already been found in the weeks since that official start, the observatory has a name worth understanding. Because the name is not decorative. It carries the entire reason this machine was built in the first place. Vera Rubin was an American astronomer who spent decades studying how galaxies rotate. She was patient, careful, and precise in the way the best scientists always are, and what she found was something that should not have been possible by the physics of the time. The outer edges of galaxies were spinning at roughly the same speed as the inner regions. That is not how rotation works under visible gravity alone. Under visible gravity alone, the outer stars should orbit slower, the same way planets far from the sun move more slowly than planets close to it. But Rubin's data showed the outer stars keeping pace. Something invisible had to be providing extra gravity, holding these galaxies together from the outside in, something that gave off no light and left no direct trace except the gravitational fingerprint it left on every galaxy Rubin measured. That invisible something is what physics now calls dark matter. It is estimated to make up roughly a quarter of everything in the universe. We have never detected it directly. We have only ever seen what it does to the things around it. Vera Rubin did not discover dark matter in the sense of touching it or isolating it. She was the one who made the case so carefully, so thoroughly that the scientific community could no longer avoid looking at the gap her numbers described. Her career was built on watching the sky and trusting what the measurements said, even when the measurements led somewhere nobody had expected to go. The observatory that carries her name was built specifically to continue that work. Dark matter, dark energy, the mysterious force that appears to be causing the expansion of the universe to accelerate rather than slow under gravity as it should. These are the two largest unsolved problems in modern physics. They are also two of the central science targets of the 10-year legacy survey. By tracking billions of galaxies over a full decade, watching how they move, how their light shifts, how the large-scale structure of the universe evolves over time, scientists working with Rubin's data are hoping to finally generate measurements precise enough to tell us something real about what dark matter and dark energy actually are, not inferred from what they do to other things, measured, characterized, constrained. That is the goal the survey is pointing toward over a decade. But the observatory did not wait 10 years to start producing results. It started producing results within hours of its first serious observations. And what came back from those first hours set a tone for everything that followed. During commissioning, before the official 10-year survey began, the observatory ran early optimization surveys to test the system, calibrate the instruments, and verify that everything was working as intended. Scientists were careful to manage expectations around this phase. The stated goal was to check image quality, survey speed, system uptime, and calibration accuracy, to make sure that once the official 10-year clock started, there would be no errors baked into the baseline that would propagate through a decade of data. That was the stated goal. What actually happened in 6 weeks of testing was that the telescope discovered 11,000 asteroids that had never been recorded before. 11,000 in a period of roughly a month and a half as a side effect of calibration work. That submission to the International Astronomical Union's Minor Planet Center, the official worldwide body responsible for verifying and cataloging small solar system objects, stands as one of the largest single batches of new asteroid discoveries ever filed. All of it came before the real survey started. Inside that group, 33 were classified as near-Earth objects, asteroids whose orbital paths bring them into proximity with our planet. None of those 33 objects posed any danger. But the detection matters because the more near-Earth objects we have on record, the better our ability to model what is out there and to react quickly if something with a hazardous trajectory ever shows up. Rubin was designed to be the most powerful near-Earth object detector ever built, capable of providing more advanced warning of incoming impactors than any telescope currently operating. Even in its calibration phase, it was demonstrating why. The same early dataset also turned up 380 trans-Neptunian objects, bodies orbiting far beyond Neptune, out in the cold, dark, outer reaches of the solar system where sunlight takes hours to arrive. 2 of these newly detected objects caught particular attention among planetary scientists. Their orbits are extremely elongated, carrying them nearly 1,000 astronomical units from the Sun at their farthest point. 1 astronomical unit is the distance between Earth and the Sun. These objects travel almost 1,000 times that distance. That is remote territory even by the standards of a solar system that already contains the outer Oort cloud. Orbits like these, stretched and distorted in the specific way these orbits are stretched and distorted, are the kind of data that researchers have been trying to accumulate for years in connection with a long-running debate about whether a large, undiscovered 9th planet might be hiding in the outer solar system. Planet 9, as the hypothesis is sometimes called, would be 5 to 10 times more massive than Earth, and would exert enough gravitational influence at extreme distances to warp the paths of trans-Neptunian objects into exactly the kinds of elongated orbits Rubin has already started finding. One planetary scientist working with this data has said that even if the survey never directly images this hypothetical planet, which would be faint enough to have escaped detection by every other instrument to date, the accumulation of trans-Neptunian objects with consistent orbital clustering would still be a significant piece of evidence pointing toward or away from its existence. The early data also allowed scientists to sharpen the known orbits of more than 80,000 asteroids that were already on the books, objects that had been tracked previously but whose paths through space were not fully precise. Rubin's high-frequency observations, returning to the same regions of sky every few nights, gave researchers the repeated position measurements needed to refine those orbital calculations. The map of the inner solar system is now measurably because of data this telescope collected while it was still technically in testing. Then in January 2026, the first peer-reviewed scientific paper based on actual LSST camera data was published. What it described was a single object in the main asteroid belt, designated 2025 MN45, that had been flagged during those early observations and subsequently studied in more detail. The object is roughly 700 meters across, about as long as 8 football fields placed end to end. And it completes 1 full rotation on its axis every 1.88 minutes. Not 1.88 hours, but 1.88 minutes. That makes it the fastest spinning asteroid larger than 500 meters in diameter ever recorded. The research team, led by Sarah Greenstreet, was direct about the significance. An object like this could not have been found without Rubin's particular combination of survey speed and sensitivity. The camera is simply too fast, covering too much sky in too short a time for a rapidly rotating object to slip through undetected the way it would with slower, narrower instruments. The paper also noted that finding this object is a preview. Once the full survey is running at capacity, astronomers expect to find many more fast rotators, each one adding data about the internal structure and collision histories of asteroid populations that existing surveys have only sampled. February 24th, 2026 was the date that shifted the mood from impressed to stunned. That night, Rubin Observatory issued 800,000 automated alerts to astronomers around the world in a single observing run. 800,000 separate flagged events in one night. New asteroids moving across frames, stars suddenly brightening and fading in the pattern of supernovae, supermassive black holes at the centers of distant galaxies flickering as they consumed surrounding material, variable stars pulsing on timescales that revealed their type and internal structure. The alert stream, which the team had described as one of the final milestones before the official survey start, arrived with a volume that even prepared observers described as overwhelming in the best possible sense. The system was doing exactly what it was designed to do, and it was doing it at a scale that forced astronomers to immediately start thinking about how to process what was coming, rather than whether the system worked. And what is coming, at full operating speed, is up to 7 million alerts per night. 7 million. Every single night. Each one representing a real change detected somewhere in the southern sky. No other observatory in history has generated alerts at anything close to this rate. The entire previous body of transient astronomical alerts across all observatories combined does not approach what Rubin is designed to produce in a single clear night. And because no human team can manually review 7 million nightly flags, the observatory operates in direct partnership with artificial intelligence, systems built specifically to sort through this flood in real time. The AI filters, prioritizes, and passes the most scientifically significant events to human researchers, who then have the option of immediately alerting other telescopes around the globe to turn toward whatever Rubin just flagged before the event fades. This is the architecture astronomers call multi-messenger astronomy. Multiple instruments, multiple signal types, multiple observatories operating as a coordinated network with Rubin functioning as the detection trigger. When Rubin spots a supernova brightening in a galaxy 3 billion light years away, other telescopes can be on. Target within minutes. When it identifies a near-Earth object on an unexpected trajectory, follow-up radar observations can be scheduled before the window closes. When it detects a gravitational lensing event, where the gravity of a foreground object bends the light of something behind it in a way that might reveal a dark matter structure. Invisible to any other technique, specialists in lensing science receive the alert before the alignment shifts. The speed matters for everything from planetary defense to fundamental physics. A supernova does not wait for observers to schedule time on the right telescope. It brightens and fades on timescales of days to weeks. Rubin catches it on night 1, and the network responds on night 2. That is the design. And it works because the telescope never really looks away. Revisiting the entire southern sky every 3 days means that almost nothing transient happens in the southern hemisphere that does not fall inside a Rubin image within 72 hours of occurring. Phil Marshall, the deputy director of Rubin operations for SLAC, described the whole arc of this project simply. He said it took 20 years of hard science, engineering, and determination to reach the point where the team could finally call action and start rolling on what he called this blockbuster movie of the universe, and that the millions of alerts generated in just the first months of testing already proved the observatory is functioning exactly as intended, a discovery machine that is fully assembled and finally switched on. The formal 10-year legacy survey began on June 30th, 2026. The decision to officially start was made after a careful operational review covering image quality, survey speed, system uptime, reliability, and calibration accuracy. Those words, spoken by Željko Ivezic, the head of LSST and a University of Washington professor of astronomy, matter because they describe the reason the start was delayed past earlier projected dates. The team chose not to begin the 10-year clock until every part of the system was performing at the level the science required, because every image from night 1 is a reference point for everything that comes after. Errors in the baseline do not stay in the baseline. They propagate through 10 years of change detection. The review process was not caution for its own sake. It was the thing that protects the integrity of a dataset that is supposed to remain scientifically valuable for decades beyond the survey's end. What those 10 years are expected to produce is a number that requires sitting with 20 billion galaxies, not cataloged, previously, not rediscovered, not counted again. 20 billion galaxies currently sitting in the southern sky with no record of their existence, waiting to show up in Rubin images and enter the permanent catalog of known objects. 17 billion individual stars in our own Milky Way and surrounding galaxies. 10 million supernovae captured as they happen over the course of the decade. 6 million solar system objects. And across all of that data, the gravitational fingerprints of dark matter embedded in the distribution and motion of those billions of galaxies, available for the first time at a scale and precision that previous surveys could not approach. Mike Brown, a planetary scientist at Caltech who has watched this project develop over more than 2 decades, said that working with Rubin's data now feels like something he could only have imagined in graduate school. Not because the data is impressive, though it is, but because the questions it can actually answer are questions that have been sitting unanswered for the entire span of his career. He also said something worth carrying out of this. If you asked 50 different astronomers what they are most excited to find with this telescope, you would get 50 completely different answers. A cosmologist would say dark energy. A planetary scientist would say Planet 9. A stellar physicist would say supernova precursors. A galactic archaeologist would say the fossil record of how the Milky Way assembled itself over billions of years. A gravitational wave researcher would say the optical counterparts. Demerger events. 50 scientists, 50 fields, 50 sets of questions that this single survey was designed to address simultaneously every clear night for a decade. And all of that, every discovery named in this video, every asteroid and trans-Neptunian object and record-breaking fast rotator and 800,000 alert night, happened before the official survey started. The 10-year clock only started on June 30th, 2026. Everything before that was commissioning, calibration, and testing. The actual science has not yet had weeks to run. What is in the data from the nights that have already happened since the survey started, the images the telescope has been taking, every 40 seconds since June 30th, will not be fully processed and available to the scientific community on a timescale that makes for immediate headlines. Science does not work that fast. What Rubin detected on any given night this past month is working its way through pipelines and alert systems and researcher review right now, today, and the papers describing what is inside that data will start appearing in the coming months and will continue appearing for years. But the machine is running. It has been running since June 30th. Every 40 seconds, another image. Every clear night, another 20 terabytes. Every 3 days, the entire southern sky scanned again. That will not stop for 10 years. And somewhere in the data it has already collected, in the weeks since the survey officially began, there is almost certainly something that nobody predicted. Something that required this specific combination of speed and sensitivity and coverage and time, domain depth to see. Something that does not fit the existing models of what the sky contains or how the universe behaves. Something that somebody, somewhere, is going to spend the next several years trying to understand. That is not speculation. That is what always happens when a genuinely new instrument turns on and looks at the sky more carefully than anything that came before it. It has happened every time. Rubin is not an improvement on existing surveys. It is a qualitative shift in what is observable at all, and it started officially 47 days ago. The movie is running. And we are in the opening credits.